You're watching Dr. God's Technique.
We have reached the point where all of our speakers have had their first pass, and now what I would like is, if the audience is willing to sit for a half an hour, we will have the panel talk amongst itself, if I can use that mixture of singular and plural, and then we will break again for 10 minutes, and then we will have audience interaction. So we'll go for roughly half an hour with panel members asking each other questions in a sort of an undisciplined free-for-all. Go ahead.
Well, since I was asked, can I start? First of all, I certainly wouldn't want to stimulate neurons because there's the end effect of a neural circuit can often be described much more simply than describing the work of the individual neurons. So this is based on various vision algorithms mostly. In fact, things like the insect tracking is done by robots with far less computing power. For instance, the Carnegie Mellon Nav Labs, one of which drove across the country, was able to track roads, and there was a certain control algorithm which keeps it on the road, which isn't very different from the Optimo thing. And it was a less than 100 MIPS machine. It was about 50 MIPS running that. And the algorithms that I expect to be controlling this general-purpose robot will, in fact, have been developed over nearly 10 years in a large competitive industry and be quite efficient in their use of those, 5,000 MIPS or whatever. So it's a matter of squeezing every last bit.
What happens when the robot gets off the road?
It recognizes most of the time that it's not on the road. It has a library of road cross sections. It stops.
Just like the lizard.
Well, the thing is, if you want something that progresses without stopping, that's just a small change in the programming. Indeed, there are generic algorithms that drive machines off road. So you're picking particular behaviors and saying this particular machine doesn't have that particular behavior, but in fact it could have.
The lizard is a really autonomous device. The lizard is a really autonomous device that manages to refuel itself, take itself through terrain that it hasn't even seen, managed to go on, survive day after day in very unusual circumstances. I don't know any robot at all that's even as autonomous as an ant.
And in fact, we don't have the computing power of an ant, really. But anyway, also we don't have the genetic machinery, which is sort of an independent underlay, which is used, for instance, to digest food. That's a mechanism that I don't expect to be in these cleaning robots. So basically, what I'm saying is that we can make these specific machines with these specific functions, which are evolved by an economy to do the particular things they're supposed to do. If you wanted to evolve a machine that could take care of itself most of the time out in the open, I think we could, but I don't think there would be the incentive to do it.
Well, first of all, let me take issue with the contention that software hasn't grown exponentially. I mean, I've been in the software industry for 40... Hello? Yeah. I've been in the software industry for 40 years, and the kinds of software systems that I see my teams deal with, and I'm not bragging about my teams because I think the kinds of systems that teams I'm involved with are developing, and I'm not bragging about my teams, they're really just competitive, but software teams in general, the productivity per person has grown exponentially. We create with very small teams of people extremely complex systems because the infrastructure of tools has grown along with the requisite hardware. Now, it's not my contention at all, nor is it Hans, that MIPS alone automatically gives you intelligent behavior. I think you've got to look at developments in many different fields. I'm encouraged by the fact that those brain regions which we have maps of and have at least some idea of their structure, that we can understand the algorithms, which are very different than the algorithms we see in conventional computers. They're digitally controlled analog. They're massively parallel. They're based on self-organizing paradigms. But we can understand basically what's going on and recreate them. And there are many examples. I think I mentioned earlier Carver-Mead's vision chips, which perform very comparably to a biological retina. The systems that Dr. Holland described in terms of neural nets are really not state-of-the-art systems with no feedback loops that are organized in simple layers that only have a fan-out of a factor of 10. We're already substantially beyond that. I mean, this is the field that I've worked in for 35 years. Fan-outs are at the next level of magnitude, more like 100 or even higher in some cases. Systems that have the kind of very organic feedback loops and interesting, intricate architectures that we see in biological systems. And indeed, we get much more intelligent behavior, and these are more challenging systems, but that is the state of the art. The future is not simply a function of MIPS. It's an interaction of more powerful computers, more powerful brain models, more powerful self-organizing systems, more powerful genetic algorithms. If you have a genetic algorithm that has a fixed chromosome, you're only going to get certain type of behavior. But what we see in biological evolution is that the meta-evolution also evolves, and that biological systems will develop new chromosomes, and they'll change the functions of the genes, and so on. So you need more powerful genetic algorithms that can actually evolve the methods of evolution. And copying or reverse engineering the brain is only one paradigm. I think we'll see an interaction, as we already have today, between biologically inspired models, understanding how the brain works in certain instances, and that will grow enormously more powerful as we can scan the brain with higher resolution. Just more powerful experiments that we do on our own in terms of artificial intelligence. I'll leave it at that.
I'd just like to ask a question of the audience, which is, how many people think that in nanotechnology the advantages to the offense? And the advantages to the defense?
And how many people think it requires further investigation? I think this is an important issue. The only thing that I've been able to think of, I think that it's likely it lies with defense if the defense has a greater resources of mass, energy, and can preposition forces. But that's a speculation at this point. I think when I get into the detailed measure, countermeasure, countermeasure, I cannot evaluate the outcome. And I think to evaluate that outcome not only requires a base of research, which provides the specific capabilities of the systems, but also a very deliberate analysis. Now, there's an interesting question as to how much of this analysis we wish to take place in public and how much of this analysis we wish to take place a little bit more discreetly. If there is careful analysis of the measure-countermeasure sort of situations, do we want to move